Okay, hi everybody, this is Caleb Carlson, and in this video I'm going to be showing you how to set up, run, and view benchmarks or storage performance benchmarks on a cluster of nodes using a few tools. Specifically in this video I'm going to be showing a Lustre file system storage benchmark. So let me show you the setup that we have first before we jump into it. So the setup that we have two nodes here, and there is a networked file system mounted to /home. It's 5 terabytes of storage, and that's where everyone's user home directories live. This is kind of critical so that we can share binaries and configurations across nodes without having to replicate that on each node. It just lives in the home directory. The second thing that we have here that's important is the Lustre file systems themselves. So this is a disk-based Lustre file system, and it's got two InfiniBand HCAs, the channel adapters. These are HDR channel adapters configured in multi-rail, and there's 643 terabytes of storage there. And then on this node, there is, or this storage system, this file system, this is a flash-based Lustre file system with 4 HDR HCAs configured in multi-rail, and it's got 4.7 petabytes of storage available. So the first thing you want to make sure that you've done is that you've gone ahead and you've created a directory for yourself. You can see here I've just got a C Carlson directory under /mount/cstore1. Because I'm going to be using the flash-based file system for our benchmarks. The next thing that we want to do is we want to go ahead and get a way to measure system performance in real time. So what I'm going to do is I'm going to go ahead and jump over to this tab where I have my user home directory. I can just show you this is under /home/ccarlson. So this is the NFS file system mount. And I'm going to go ahead and go out here and clone this Omniscient tool that I wrote. So git clone on this guy. And that's got that installed. So if I go ahead and jump into setting up this Omniscient tool, essentially what this does is I'll just run omni help. This just runs a monitor across all the nodes that you're interested in monitoring, and captures basically snapshots at different intervals. And at each snapshot, it captures what you can configure for different metrics. So if we head over to setting this up, let's go into the config directory. There's two files here. There's host.txt. So I'm going to go ahead and jump into host.txt. And this is just a default template, a list of the hosts that you're wanting to monitor. So instead of N01 and N02, I'm going to go ahead and put the two nodes in that we're actually going to be monitoring. And then next to this is the directory where you want the capture metrics to go. So on each node, it's going to be taking the snapshots, and those snapshots are going to be being dumped into files, and this is where those files are going to live on the individual nodes. So now that we've got that set up, let's go ahead and crack open the config.sh file. This has just got some different parameters that you can tune to your liking. Total snapshots, we want 300 total snapshots because at 1 second intervals, this is about 5 minutes of measuring the system's performance. And you have some toggles here. I don't want to capture memory metrics in this test because I don't have that implemented yet. But I do want to capture nmon stuff. So nmon is like stuff like CPU usage, disk pressure for local disks, and some other stuff. It can also measure normal networking, so normal networking that you get through the kernel, the normal IP stack can measure that, but it can't capture things like InfiniBand, which bypasses that, bypasses the kernel. So I've got this other tool, InfiniBand monitor, IBmon, and we want to turn that on. The next thing here is the InfiniBand devices that we're going to be capturing. So this is just a comma separated list. I'll go ahead and set the devices. These are the MLX5 device names for the high-speed channel adapters, or the host channel adapters. Oh, this should be 4. 0, 1, 2, and 4 are all HCAs on the system that have valid lids. So if I go ahead and run ibstat, you can see here we've got 5 total InfiniBand cards. These are ConnectX-6 NVIDIA or Mellanox cards, and they've got lids except for MLX5_3. This is not set up correctly. It's got a base lid, a local ID of 0, and it's not set up to be a 200 gigabit card. So we just want to use the 4 MLX5 0, 1, 2, and 4 cards. Okay, so that's configuring the Omni variables. We want to, for simplicity's sake and just for our own sanity, go and add this to your bash RC wherever you're going to be running it from. I'm going to be running this as root because I want to be able to use InfiniBand monitoring, which needs root access. So I've got down here, I'm just going to go ahead and export the Omni path into my path variable. So I've got home, C. Carlson, Omniscient. And go ahead and source that. And now you can just run Omni directly without having to go to that exact directory. Okay, so the next thing that we want to do is go ahead and now that we've got Omni laid out, we want to go ahead and run omni init. And what this is going to do is that's just creating the directories, the individual host directories where metric snapshots are going to be stored. So we've got one for each of the nodes. Now that we've got the benchmarking or the monitoring tool set up, let's go ahead and set up IOR, which is what we're going to actually use to run our benchmarks, our performance benchmarks. So I've got here git clone HPC IOR. And now you can see I have both IOR and Omniscient in the home directory. So if I go ahead and go into IOR, it's not really configured or installed yet, but the process for doing that is just running bootstrap. And then once this is done, run /configure. Once that's done, just run make and ignore the warnings. Okay, what that's done is that's just generated this source directory and has compiled IOR into that source directory. So now we can use that from our launch node. I'm going to call it the launch node. This is just the first node on root file system. We can use that IOR if we want to by invoking home C. Carlson IOR/source/IOR. And if we just run --help, we'll get all the options. The next thing that I'm going to show you how to do is actually how to run the benchmarks. So I'm going to go over to my notes that I have, my documentation. I just did this IOR installation. I'll post a link to these notes so you can follow this if you want to. But down at the bottom here, I have a script for parameterizing and running all the IOR benchmarks. So I'm just going to go ahead and create a new shell script here. And what's important about this shell script is making sure that your variables at the beginning are set correctly. So this IOR binary variable, this is the location of where that IOR binary lives. And for every node, it's going to be the same path because we have a network file system. So it's just the home, C. Carlson, IOR, source, IOR. The next thing is this machine file. So we're running this IOR binary with MPI run. It's kind of equivalent to running like with parallel distributed shell, except MPI run uses obviously message passing interface to invoke the IOR binary. And it needs a machine file which just lays out what machines it's going to be communicating with or controlling, and then how many slots that it's going to be, or really parallel processes on each machine it's going to be running. The total hosts, this is just listing the total number of lines in this machine file, and then the total slots is multiplying them by how many slots you want to run on each of these machines. So what I'm going to go ahead and do is back out of this real quick and go ahead and create this machine file. So creating this machine file.txt, I do need the host name, so I'm going to copy that. Okay, so I've got the host name, and then you just want to put in here how many slots you want to allow this machine to have. I'm going to give it 64 slots because there's 128 logical CPU threads and 64 physical cores. I'm going to go and copy this again and change this second line to the second host name because we just have those two machines. Going back over to the benchmark.sh script, this block size per task, essentially this is for every one of those individual processes that are running in parallel, how big of a file do you want it to write? Or how big of a file do you want it to read as a block? Then going on here, we have transfer sizes. So you could have different amounts of transfer sizes. For example, this is how big of a transfer size do you want it to send on the network at a time as a transaction. I found that good values here are usually around 64 megabytes for the way we've tuned our Lustre file system. The test directory, this is where in the Lustre file system we're going to be writing our files, and then the test file is what are we going to call the base of our file name that we're writing out for each process. I have functions here for each of the different tests you can run. I have a random read test, a sequential read test, a random write test, a sequential write test, and each of them essentially just takes in a transfer size as a variable or as an argument and runs MPI run, obviously allowing MPI to run as root. You pass in the machine file to MPI run, and then you give a number of processes, the total slots that you want to map across all the nodes. So that total slots is, remember, the total amount of machines times the total amount that you want each machine to run. So I'm going to change that to 64 because we only allowed 64 slots per machine. Then we want to map by slot, so we want to divvy up the tasks across the machines by slot. We want to, the second part is, what do we want MPI run? So this is all what MPI run is configured with. What do we want MPI run to be executing on each machine? And that's going to be the IOR binary, and we want to put it in verbose mode. We want to run it a file per process. We want to set the POSIX ODirect flag out so that we're not using the buffer. And then there's just a bunch of other options here. Here's the transfer size. Here's the block size per task. We want to write. We want to save the files that we write and not remove them afterwards. And here's the output that we want to write. After all this, we're not going to write this as standard out. We're going to write it to a file called whatever your benchmark was, underscore the transfer size that you're using. In case you're using different transfer sizes, you'll have different files as the outputs. Here, I'm just going to demonstrate the sequential write. So I want to comment out everything but that guy. And then I want to go ahead and make the benchmark script executable. Okay, now that we've got the benchmark all set up and ready to go, what I'm going to go ahead and do is run omni start. And what this does is started a monitor with this ID. Remember this ID, and if you forget it, you can run an omni list, and it will show you the running and stopped monitors on each host. And obviously you can see here, this got the monitor ID for each of the monitor types that are running. The next thing now we've got our performance monitoring tool running is we can go ahead and start the benchmark. So just launch benchmark.sh. And this will run for about a minute. And when it's done, it will output the results of the IOR run to that sequential write file. Okay, this looks like it's finished up just now. We can go ahead and stop our monitor that we're running across all of the nodes in the cluster. So go ahead and run omni stop and then give it the monitor ID. You'll see this is all the things, this is all the processes that it stopped. And let's go ahead and see what it output. So we've got this sequential write 64 meg .out file. Let's go ahead and break that open and see what's in there. So we can see here that we're not getting the best performance. We can get a lot better performance, but this is really just for demonstration purposes. It's not for showing you the best thing that we can get. It looks like right now we're getting about 35 gigabytes per second aggregate average write speeds. This is the IOR output. We can go ahead and collect the omni output by specifying I lost it up here, the monitor ID, and then I'm just going to go ahead and give it an output directory that I want it to write to. So this is going to collect all the results from the individual nodes so we can look at the performance. I have my experiments directory, and I'll just go ahead and call it example. Okay. This collect all the nmon CSV results and the ibmon CSV results and merge them all together. And so in that case, we've got this example directory. I'm going to go ahead and just tree it. This is what we've got in there. There is, I'll go over the structure of this. There is per node, there is a set of individual files per node per InfiniBand device that was being monitored. There's also a per node nmon CSV file that's looking at things like the CPU, the local disk writes and reads, so on and so forth. Then there is a aggregate InfiniBand monitor CSV file per node per monitor ID. So this takes the results from all of these guys and it joins them together and sums up the performance metrics to show you per node performance. Then lastly, there's a total aggregate ibmon CSV file, and this is showing you the entire cluster's InfiniBand performance, all aggregated together. So what we can do now is, this is kind of the end of your experiment, but now you have to go visualize the results and kind of parse through all the data. So what I'll go ahead and do is I'm just going to go ahead and just get this one guy over to my cluster benchmarks repository. This is also public. The Jupyter notebooks are published out here if you go to cluster benchmarks. I've got some just Jupyter notebooks for visualizing different results. It's pretty concise. But what I'll go ahead and do is just show you through this. So here I have the list of nodes that I care about in this experiment. The monitor ID, so I'm going to go ahead and change this to the monitor ID that we were using here. And then I want to go ahead and just SCP that file over to my current cluster benchmarks example directory. So we've got that file right here that just showed up. And I'm going to go ahead and, now that I've already changed this monitor ID, it should reflect that in this pandas data frame. So what I did was I just loaded this into a pandas data frame because it's a CSV file. And you can look through all the different columns here. There's a column per node's InfiniBand device. There's a column per node. that's aggregated, and there's also a total aggregate column all the way over to the right, where you can see things like the data that was received across all the nodes in a summed aggregate form. This is a lot to go through. If you want to look at the raw numbers, you can look at it in this form, but we want to plot this because that helps us visualize it better. So here I've just got a matplotlib, 1 row, 2 columns plot, and I'm just plotting the nodes and their transmitted data is what I'm caring about for showing this. So here's our experiment. It's not the cleanest. It could be, the graphs could be organized a little nicer, but this just gets you started with how do you visualize the results that you got. Here's each of the nodes, 1 graph per node. You could either make a big graph and put all the plots together, but this just kind of shows you that each node, like this node at its peak was transmitting about 40 gigabytes a second. This node went up to about 30 gigabytes per second, and this is what it took to get the job done. So hopefully that helps you see how you can view this kind of stuff, and gives you a better idea of how to install IOR, install Omniscient, and visualize your results. Thank you for watching.